G'day, I'm Beth Fulton. I'm the person who wrote Atlantis, and I'm going to be taking you through the Atlantis course over the next few sessions. This particular talk will go over the course structure and then a general overview of Atlantis to give you a very brief history of Atlantis. It's a science-based piece of software, so it has its quirks, and I apologise ahead of time that it can be difficult to use, but I try not to hide that from people. It started off as a part of my PhD more than 20 years ago now, and it was a way of synthesising ecology of ecosystems and to understand how human interactions with them, such as fisheries, how they affect them and how we might go about mitigating and managing that. So I will start off with a few warnings. There will be some swearing potentially. I try not to swear. My mother gets upset with me, but it kind of comes out of habit, so I apologise ahead of time. If you find that confronting, I will try to keep it to a minimum. I do expect the course to be hands-on, so I'm hoping you'll be able to not only look at these presentations, but actually start to play with the model and understand how it's put together, how best to go through calibrating it, and then how do you interpret its output. I also apologise beforehand if you can hear any roosters in the background. I live on a farm and they're not particularly quiet or subtle creatures. We do expect to hear lots of questions through the course, both Javier and I, so that's why we're trying to structure the sessions around having quite a large question and answer, because it really is a lot about trying to share our learnings rather than something that you can learn out of a book. And we will ask you to look at code. So for some of you, you might find that very confronting. It's not scary. It's just like reading a book or in a slightly different language. So there will be some learning curve for sure, but it's not a terrifying experience. In the first session, the first Q&A panel when we get together, I'm going to ask you to introduce yourself. So I'll start off here. I'm Beth Fulton. I'm based in Tasmania in Australia, or the arse end of the world, as I lovingly call it. Right now, in the midst of COVID, that's probably a great place to be. My interest is, I'm a mathematician by training, but also an ecologist. I have a very broad interest in complex systems, socio-ecological systems, so how humans and nature work together as part of bigger systems, how they're all interrelated, what are the functions across many different scales. But ultimately, how do we take all of that understanding of how humans and ecosystems work and take that to a place where we can get better sustainability, better management, adaptation to climate change, all of those kind of applied questions. So I do have a theoretical interest, but I also have an applied interest. In terms of why we look at marine ecosystems, they have a range of values. Some of those are purely economic. They provide food, they provide employment, but for many thousands of years, they've also created a sense of purpose, a sense of wonder, and they're very valuable in a cultural sense to all nations pretty much on the planet. There's also recreational pleasure today. It's not just about commercially exploiting it or having a religious experience. There's people, well, in Australia, 87% of people live within 50 kilometres of the coast and visit fairly regularly, really. So there's many reasons to value marine ecosystems. But they're under a huge pressure. The use of ecosystems is going up exponentially right now. So as we've used up the land, now we're moving into the ocean. So we need to understand how to do that wisely to avoid the kinds of problems that we've seen on land. And Atlantis is just a small part of that. It's not something that's going to be the be-all and end-all. It's not a panacea. It's not something you can use by itself. But it is a part of a bigger jigsaw puzzle of how science can provide evidence into things like fisheries to help structure our understanding and to help structure what that management might look like. So I'm a very big advocate for evidence-based and science-based decisions, and Atlantis is a part of that, particularly at the strategic scale. There is questions of whether You can use it at a tactical scale, so a year-to-year, day-to-day kind of decision-makings. And I'd have to say, in the main, no. It's really much more a strategic tool of the big picture thinking of what the whole system might look like. Around the world, it's being used for a number of different purposes now. There's more than 500 registered users, so I'd have to say that the actual active pool is much smaller than that. There's a good deal of turnover. People use it for a purpose and then move on. There's some long-term users. I'm obviously one of them, but there has been used for a broad range of questions. Fisheries primarily, by far, but increasingly into multiple use management, a little bit into oil and gas in its mitigation. It has been used in the Great Lakes, not just in the ocean, so both in Lake Victoria and the Great Lakes of North America. It's been used to look at biodiversity and climate, hypoxia, port development. So there's quite a wide range around the world, but I'd have to say fisheries is its primary consideration, or seafood production is its primary consideration. It's based around the concept of adaptive management. So that's where you lay out your plan, you implement that plan, you monitor how well it's going, you evaluate the outcomes and whether they were what you expected, and then you either adjust those management plans or you go back and review whether you're on track overall. It really exploits what they call double and triple loop learning that happens, or it's the best practice learning method now in education. It sort of converged on that by accident. It was developed within resource management to actually try and get action, but it has proved to be one of the most effective ways of dealing with uncertainty. It's not easy, and it does require that adaptive loop, which not all political processes are comfortable with. But it is a good way of thinking about how to manage the world, and so Atlantis breaks itself down in the same way so that we can replicate that adaptive management loop and understand where the strengths and weaknesses of its application are. One of the great reasons to do it in a computer, though, is you can test lots of different implementation ideas and even plans simultaneously and learn, at least in model world, what will and what won't work and where some barriers might be. And so that can shortcut the learning process. It can help in places where it's a one-off decision, like a port development, but it can also highlight where there might be effectively like a flight control, when you learn to fly planes and stuff in a computer, a simulator. You can do that with management in effect, and you can figure out where the weak points are and try and strengthen them before you actually do it in the real world. So that's the structure of Atlantis. It has a physical component that underlies an ecological component. They're dynamically connected, and that makes up the model world. In management strategy evaluation speak, that makes it the operating model. So that's your version of the world. On top of that, you've got the exploitation model, so how the humans interact with that system, how they take materials out of that system, for instance, how they catch, how they take out mining materials if you're worried about that. But let's just stick with fisheries for now. So how do they catch? How do they move about the system and catch the fish? From there, you've got representation of the data collection process and the assessment. So that's actually called the assessment model. It doesn't have a perfect view of what's happening inside the operating model. It has all the same kind of sources of errors and issues that you would have in real world about the data collection and assessing the system. On top of that, you've got the management decision-making process, which can be influenced by, but also influences the socio-economic system. So you can even have political lobbying and stuff like that in if you want. But the basic idea is you have an operating model, which is your representation of the natural world, and you have the human part of the system with all its warts and the fact it doesn't have a perfect knowledge of the natural world, so that you can test out where the management strategies and that uncertainty, how do they work together? Can you get a good sustainable outcome without having perfect knowledge? And so you run through multiple different versions of that. So you've got multiple different versions of the assessment model, of the management model, even of the biological side. So you can check for what they call structural uncertainty. So it's not just about parameters and how they may vary and influence your uncertainty, but it's also how's the world put together? How does that influence our understanding of uncertainty also? At the other end, what you do is you're not trying to optimize. It's not an optimization process at all. You discuss with people ahead of time not only the strategies they want to try, but what are their objectives? What measures have they got to meet to make this successful? And it's not just from one group typically, it's from a broad range of stakeholders, whether they're First Nations people, recreational fishers, commercial fishers, regulatory managers. You can even go into the broader community about their opinions, bank managers, you can take it as broad as you like, but on the basis it usually has the fishermen themselves, the managers, and those that are otherwise directly influenced. And they all lay out their objectives, and that's a big discussion point, and that can actually be some of the hardest part of doing a management strategy evaluation, is getting people to define their objectives and then discuss the different options about what they want to do. You then run those options through the model, so in this case Atlantis, and it comes out with values for the different indicators that you've mapped to your objectives. So you often don't have a variable that delivers directly to an objective. So your objective might be, have your stocks sustainable. So you then have to infer that from the biomass levels. So you'll be tracking biomass and you map that back to sustainability. So you look at the level of your different indicators in the output of the model, and you see whether they meet the objective. So in traffic light sense, whether it's a yellow or green, or whether it completely fails, which is a red. And what you're looking for is a case where you don't have red across the board, because that means no objectives have been met. But equally, it can be pretty dangerous to have something where some objectives are met really, really well, but other objectives completely fail. While in the real world that often happens, it's not actually something that's delivering to what you want. If you can get green across the board, that's great, but it so very rarely happens. What you tend to have to do is find compromises where everybody's had their minimum requirements met, but typically no one has had all of their maximum requirements met. That's a pretty high bar to reach. We call that minimum sustainable whinge. Everybody's a bit happy, even if no one's completely happy, but it's usually the best compromise you can come to. In terms of what goes into each bits, there's quite a bit, and I'd have to say right now that there's kind of two versions of Atlantis. There's the version I share with everybody else, which tries to be as bug light as possible. It's not completely bug free, I'd have to say, probably. We try to keep it bug free, but there's always sneaky new ones that we find. And then there's a version that I play with, which is a bit more explosive. In the sense it's got a lot more developing features in it, but probably a lot more bugs too. But in the main, these are the processes that are in there. There's the main oceanographic processes, the main geological processes. There's a lot of attention to ecological processes and different variants of that, from the nutrient cycle up through how food webs function, but also with some individual activities in there as well. It does have biodiversity and evolution in there in a simple sense, though that's not widely used yet. On the human side of things, it does focus primarily on fisheries, though some of those other sectors can be represented either dynamically or in a light kind of way. In socio-economic sense, very few people actually use that beyond me, but there is the capacity to have, at least for the fisheries, a lot of the socio-economic drivers of behaviour included. And then on the assessment and management side, again, much more focused on fisheries than anywhere else. You've got the capacity to represent harvest control rules and the management regulatory responses. In terms of assessment, it includes or can link to most of the major assessment methods for fisheries, but it also mimics scientific independent surveys. So that can be useful for exploring where you might have gaps and problems in those. In terms of that management cycle and what that means, wrong way. you're basically looking at system structure and function. You can look at impacts of change, whether that's large or small scale, particularly climate change. You can look at whether your assessments are reliable, what kind of management is most robust and works. People are starting to think about social and economic, but those kind of questions that I just highlighted then are the most common types that Atlantis is used to think about. Now, what's inside a model? I'll do this fairly at a high level because we're going to go into more detail over the next few sessions into specific components. So at a very high level, Atlantis has a polygon structure, so you'll notice that it's not on a regular grid. It has funny shapes to define its maps. And those funny shapes need to be matched to the bathymetry of the system, where major current flows go, where there might be natural breaks in the biogeography of the system. But the basic rule is have a big box where things change slowly or can be statistically summarized, and have a little box where processes change very rapidly. So as you go over a steep slope or around a seamount or into a bay, those kind of features need to be pulled out in small boxes, whereas large areas where there might be a huge eddy, but it is a large oceanographic area that's relatively well mixed, that can be represented by a single box type, a large box, sorry. Now within each box there is a three-dimensional structure that I'll get to in a sec, but at the very bottom end of that is what's the geology doing. So that's a very simplified geology. You can have different grain sizes if that's your thing and you're worried about resuspension. But in the main, we just break it down into what's rough ground, so rocky ground, reefy, what's flat, so that's so pebbles or large pavements or hard compacted stuff. And then you've got the soft stuff that can move around, that in fauna in particular love to live in and among. So that might be silts, muds, sands. So we just break it down as the proportion of each of those. Then superimposed on that is another proportion, which is the proportion of it that's a canyon. And that's because those areas tend to magnify or bioenhance what's happening. So they act as a multiplier. In terms of the three-dimensional structure, within each cell you have multiple layers. They don't have to be the same width. You can see here there's quite a number of thinner ones at the top of that picture there, and larger ones as you go further down. That's fairly standard. Sometimes you also have another couple of layers that are thin right near the bottom if resuspension is something you're worried about. You'll also note that you don't have to have the same number in every box. So if you have a hydrodynamic model, they often have the same number of layers in every grid cell, and then they squish them down so they're not as wide when they come into shallower water. We've kind of jumped the other way, where they don't have to be exactly the same depth in every box, but typically they are. So you might have just a couple of layers in shallow water and then have more layers as you go into deeper water. Again, you need to just break that up in whatever layering makes sense for your particular system. You can have multiple sediment layers too. Most people don't. Most people just think about the top, usually oxic sediment layer, but you can have multiple sediment layers as well. And you don't actually have to have layers that go all the way to the bottom of the ocean, particularly in the deep ocean. You can have what they call an open boundary layer at the bottom, where you just assume some mixing from the deep ocean up into the bottom of the water column. Now, in terms of how those layers are numbered, if you think about the epibenthic layer, so the surface of the sediments, that's your dividing line. The 0 starts there. Then you count up through the water column till you hit the surface, and you count down through the sediment till you get to your deeper sediment layer. And that's just because of the way the code is written. It's easiest to assume that structure. I'm sorry if that creates confusion in putting together your initial conditions, but that's the structure to keep in mind with regard to how things are ordered in Atlantis. And all layers start with layer 0 because we're right in C, which assumes a 0 point to any arrays. In terms of how hydrodynamics are done, you pull in exchange rates from typically a hydrodynamic model, and that moves water around in bulk from one box and layer to another. It can go both vertically and horizontally, and you can have, depending on your time step, you might have a single box layer feed off or get influence from many other boxes and layers, because you're representing an aggregate exchange over a period of time of, could be 6 hours, 12 hours a day. Most people don't use a week or a month anymore. It's typically 6 to 12 hours, but you can still have quite a number of exchanges, particularly if you're in a smaller area. At least in the past, upwellings weren't necessarily well represented in a lot of hydrodynamic models. That's getting better as models are more developed, but you can put in additional upwellings of your own if you want to better represent what that looks like. In the old days, we used to have to try and estimate some of these exchanges off raw satellite and current data. You can still add in by hand or by assumption some options for mixing, and Atlantis will allow you to put on some what they call flags. So every time we want to turn on an assumption in Atlantis, there's a flag. We'll explain that structure maybe a little bit more in person when we get to the file structures. But basically you need to configure Atlantis to let it know what it needs to do code-wise. One of those is whether you want to have Atlantis deal with some of that mixing or whether you're going to feed it all in from a hydrodynamic model. These days what we tend to do is hydrodynamic models are much more common, both in local scales and in the climate world, so we suck in data from those. So you have very fine scale hydrodynamic models, and from those you don't try and dynamically link them. At the present moment we just run the hydrodynamic models, or typically another whole science group is running a hydrodynamic model, and you get off them the raw data, and then there's a process that Javier and I can talk through about how you then get from that what the water exchanges are, but also what the ambient salinity and temperature per layer per box is. You can also include some eddy structures that way as well, which is another amplifying factor, but the very core that you need is water movement, salinity and temperature. In doing that, you have to be aware of what the water movements are doing. So because it's not a fine scale grid, it's those polygons, what that means is that you run the risk of having excess diffusion. So that's when something gets mixed much more quickly than it should in reality. And now, because Atlantis has polygons and assumes it's well mixed within a polygon, as soon as a particle, so say that little red dot there, moves into the blue rectangle, the Atlantis box, it's available across that entire box, which is effectively scooting it way faster than you'd imagine in any other sense. So that means that we have to back correct that in the exchange so that you're not overstating how well and how mixed things are. So that's just a part of the process that we have to think about. You can use that through very complex inverse methods. If you're working with a hydrodynamicist, they may be able to help you with that. Typically, we end up having to do a rough area correction and then do a little bit of tuning once you're inside the running model. The way that Atlantis does most of its physical processes is just through a gross slab mixing or gradient exchanges. Most of the things like bioirrigation, bioturbation, resuspension, settling, all those major physical processes, you basically take a very thin slice out of one layer and a very thin slice out of the other layer and swap them and re-average within the layer. It's not particularly refined, but it's a very close approximation to very complicated equations that would slow things down enormously. You can elaborate that and make it have the influence of, say, biology or oxygen dependency and other things like that by tweaking the lambda in that equation, so which can amplify or damp what's actually going on. The other functions that we use a lot are decay functions. So instead of having explicit burial out of the system, we let properties in the very bottom sediment layer decay away, and that works fairly well as well. So it's about using simple equations to try and mimic the outcome of very complex processes as an equation. So it's not absolutely exact. There is a little bit of smudge there, so to speak, but it's a lot faster, and given the level of uncertainty that is already in ecosystems, it sits well within that band of uncertainty. Where most of the focus in Atlantis has been, though, has been in its ecology. So the way that Atlantis represents ecology is in two ways. It has biomass pools, which are kind of aggregate lumps, and they're represented by the rectangles in this particular picture. And then you have full age structure, where you follow the number of individuals at size through age cohorts through the population, and they're the polygons there. So you can see that you can have very different age structures in different parts of the system. And then you have the feeding flow between those. Now, you might want to represent individual species of, say, commercial concern. You might want to represent functional groups of specific species. You might want to represent whole clades, or like whole huge groups, like all of macroalgae or all of phytoplankton in one lump. We tend to size structure the plankton groups a bit and have the invertebrates and vertebrates based on the functional groups, which are defined based on feeding interactions, habitat use, ontogenetic behaviour, commercial fisheries targeting, or even whether they're species of conservation concern. So such as large sharks and birds that are in the top left-hand corner, even if there's no image on here at the present moment. So the reason that we structure it in that way is that you get the functional diversity and the function of the system, but again in a pragmatically supportable way. And you can follow the evolution of a system through time then. So if we think of Southeast Australia in 1910, this was its kind of rough Atlantis structure. You'll notice in particular that there's a broad set of fish groups, and by 2000 that had changed quite a lot. So you can see the really light blue groups have become much larger biomasses. They're the mesopelagics and some of the small pelagics. The darker blue groups have become more triangles because we've truncated their age structure quite severely in some cases, as well as reduced their biomass. So you can follow the evolution of a system through time and how that can restructure, because that can reset what you think is a reasonable B0 for a system, an unfished state for a system. So those functional groups, so my blobfish on the left there is going to represent biomass pools, and then you've got the age structure on the right. In both cases, you've got predation and fishing mortality, you've got the capacity to do movement, feeding, waste, that kind of stuff. But in the age-structured one, you've got some other details around aging and reproduction and ontogenetic shifts that you can more easily represent. So in terms of what that looks like, for the age-structured populations, you have what preys around, what can fit in their mouth, so gape limitation, and then what they then ultimately are able to prey on. What they consume is split into material that supports their structural growth and their reserve growth. So reserve growth is your fatty tissue, and it's preferenced over structure. You've got to be in a healthy condition before you can physically grow any larger. Once you're an adult, some of that reserve goes off to reproduction, so that helps have that tailoring off in somatic growth, the structural growth, because more of your energy is going into reserve, into your reproductive capacity. On the waste side of things, you can have disease and oxygen limitation of your growth, and any materials that you output then go into nutrients and detritus. But also predation, you obviously can be eaten. The equation across the bottom there is quite similar for the age-structured as well as the biomass pool groups in terms of what's in there, which is basically you grow based on what you eat, which is the biomass times the availability of your prey, the alpha term, your assimilation efficiency, and then any limitation based on oxygen and the available space. Then there's lots of different kinds of mortality, whether there's special kinds of mortality to do with specific circumstances, such as an oil spill or a hypoxic event, and then you've got predation mortality on the end, and then they've got the harvest as well. In addition, there's kind of a background mortality. So that can be a linear term, as in that particular case, ML, but can also be a quadratic term, so that you've got density-dependent damping in effect. You try to keep ML and MQ to minimum, so that most of your predation, and so most of your mortality is coming from predation and fishing or senescence once you're very old. But you can use those background mortality terms to represent parts of the ecosystem that you're not explicitly modelling, and also as a little bit of a tuning parameter. So for some of the large predators, for instance, where I think we don't get some of their population and specific behaviour well, their density-dependent behaviour, there can be a way of helping constrain their biomasses appropriately. Now, in terms of the biomass pool groups, they're very similar in the way that they function to the age-structured groups. They don't have explicit gape limitation, so you do have to take that into account a bit in how you set up their prey availability in the first place. But otherwise, they function pretty much the same way as the vertebrates, but they don't have to do that reproduction, that reserve structural split. It's just the whole gross biomass pool for that whole population, or part of the metapopulation inside each layer of each box. Whereas for the age-structured groups, it's the numbers of that size in each layer of each box. So there's a slightly different representation, but the concept is the same in each. When you get to the primary producers, it's slightly different. So you'll notice across the bottom there that their production is their growth rate, but it's also influenced by the amount of available space, particularly if they're a bottom-growing macrophyte or seagrass. But also you've got nutrient limitation, light limitation. They are treated as biomass pools. You can put a little bit of age structure into, say, some of the macrophytes, but typically if you're going to have different sizes, they're split apart as wholly separate pools. So for instance, in the plankton world, you'd have your phytoplankton, your very small phytoplankton, split out from your diatoms, which are also dependent on silica and larger in size, and then you've got your dinoflagellates. We do allow for mixotrophy in the dinoflagellates, so that means you can have them be predators as well as primary producers, so we do try to capture some of those nuances of some groups, and you'll notice that they contribute a return into the nutrients that feed themselves, so we do try to do that nutrient cycle. In terms of the ecological processes, we represent the major ones, so the nutrient cycle, feeding, growth, movement, reproduction. There is a slight elaboration for specific species like corals and sponges where people have put a bit more attention into what they do, but the way that we characterise this is you think about the major actions in the ecosystem, and then we try to give you a heap of different options about how you want to represent that. And as people come along with new ideas, we build those into the code so other people can use them as well. And then we have the capacity to polish up some of those processes. So for instance, environmental forcing of larval production, or your preferences about where you want to live based on temperature and salinity and stuff like that. You can also have multiple genetic stocks, and you can represent things like evolution and biodiversity in a very simple way. The basic concept is to try and mimic the processes and how they structure the real world. So for instance, you might have a size distribution in your fish population, but there might only be one part of that that's available to a specific predator. So you're trying to mimic out all of those different steps and how that might influence things like the movement of predators through time as they move to new forage areas. In terms of the biogeochemistry representing the model, it's again a fairly simple representation, a bit like how they did plankton models in general 20-odd years ago. We haven't followed some of the more recent elaborations because it does its job for what we want, which is basically just to turn the nutrient cycle over, allow for hypoxia, and the bacterial breakdown of material. Bacteria aren't represented as predators per se, they're represented as colonizers who cover the detritus, then break it down. It's a little bit of a nuance, but it's a much better representation in effect of how they function. It gives a better sort of dynamic of bacterial biomass. We also now allow for ecotoxicology with lethal and sublethal events. The lethal is the easiest one, I think, to represent. The sublethal still gets played with a lot, trying to get it right, but it is there if you want to look at the movement of materials through the food web and how that influences both the whole nutrient cycle but individual mortality, reproduction, movement. that kind of thing. In terms of the habitat, we do allow for the representation of living habitat. So you can say you can name a group or identify a group as being habitat producing, and so other groups can then be dependent on its level of biomass. And then you can have a non-linear relationship about the size of the refuge. So basically, if the refuge is around its carrying capacity, so to speak, there's a maximal benefit to the prey species that live within that. And as the biomass of that living habitat drops away, the availability of those prey becomes much, much higher to predators, so that you get that refugia effect. You can also identify, both for living habitat and any other species, its connection to different kind of sediment types, or that rough, soft, flat, so you can say where animals live. You can do it without age structure if you want for some of these biomass living groups, but if you want to really think about the recovery of something, let's say like corals, you do want to actually put some age structure in there. Living, particularly tropical reefs, as opposed to rocky temperate reefs, have a lot more detail put into those living reefs, simply because they've been the focus of research by a couple of groups, like Mariska in Hawaii over the years. So we've tried to put in rugosity, the split between the zooxanthellae and the host organism, how it's affected by bleaching, all of those different capacities. And then Albie's put in a lot about sponges. So there is more elaboration for some of the groups. For things like macroalgae and seagrass, there's representation of things like scour for macroalgae and fouling for seagrass, so that you get the effect of having the epiphytes living on the leaves, affecting its capacity to grow. So in terms of some examples of what those different options look like for some of the key ecological processes, there's lots of different ways you can represent movement. For instance, it can be a forced interpolation of distribution on a quarterly basis, which is a great way to start the model, but often you want to elaborate it a bit more. So then you can have movement based on forage, where the food is, and density dependence. You can have sedentary species. You can have a mix of different options in different seasons. So they might be prescribed movement, migration for reproduction, whereas they're feeding and responding to forage in other parts of the year. You can also have migration completely out of the model domain for large parts of years, even multiple years now, if you think about salmon. If you're going to use some of these dynamic movement options, we have to interpolate based on cruising speed, so animals can't magically teleport around the model. So it can be tricky, and it can cause compounding effects if you haven't quite got your feed distribution right. So it does take a layered process. But we basically would recommend you to turn on the options that you need to represent the ecology of the system that you're worried about. So thinking about, you probably can't model the entire world if you're trying to do southern bluefin tuna, so you have to let them go in and out of the model, for instance. You might want to have vertical migration for some species so that they've moved with their prey items at different times of the day, like mesopelagics do. You might want to have seasonal movements if you've got a large shift in where species are in different parts of the year. So you basically tailor your options to what you need for each individual group. You don't have to use the same option for every group. Similarly, in reproduction, I think we're up to 26 or 27 different options for how you want to represent your stock recruitment relationships. Some can be completely random. They can be based on plankton, levels of plankton, because it's the feed source for the larvae. They can be based on classic stock recruitment relationships. They can be influenced by environment. You can read in larval matrices. In the main, though, what you look at is how much spawn comes out of your adult population, and then how's that transplanted and translated into the earliest of settlers that come back into the system. So you don't typically track through that larval phase. You produce your spawn, it gets all stored up to bee larvae, and then they arrive at the right time in the future. So you can define what kind of conditions they arrive into. Do they look for their parents So you can actually have live young and offspring, so for instance in marine mammals and stuff. Or are they broadcast spawners that just turn up in the right environmental conditions like temperature and salinity? They turn up in specific reef locations. You can tailor all that kind of stuff, and equally it can be different for different species groups. Consumption is probably the biggest part of Atlantis. It's certainly the biggest bottleneck in its speed with allowing everything to eat everything else. There are again multiple functional responses here. You can think of all the Holling responses, for instance. The basic concept behind it, though, is that there's an availability matrix, which is the sort of the realised, if everything is in the predator's favour, what's its capacity to eat the prey as a proportion of the total population in its location? In the sense that if it's one, it could potentially hoover up everything around it. If it's close to zero, it's going to struggle to get any of those prey. You also need to put in some ontogenetic structure. So what's the capacity of a juvenile predator to eat a juvenile of that prey species, okay, or an adult of that prey species? And equally, if it's an adult predator, what's its capacity to eat juveniles or adults of the others? So you've effectively got 4 matrices. Some people just cookie copy one to all 4. Others put a lot more structure into that. If there is strong ontogenic change, you probably want to be putting in the structure. That there will be gape limitation on top of this. So if it's a little guy, he won't be able to eat something big anyway, typically. The reason that we go to that effort and that way of doing it is that you can get different realised diets as prey and predator populations change. So, for instance, in both cases, the relative proportion of the prey available is the same. With the light being the total, the sort of the lighter, bigger box being the total biomass for that particular prey, and the darker bit what's actually in the stomach if you were to break it open and do some diet evaluation. So you can see in the top there you've got almost 50-50 split between the two prey, the orange and the green, because those two dark squares are about the same size. But in the bottom one, the biomass of the orange species has really dropped away and the biomass of the green species has really come up. So if you were to go and sample that prey, that species now, that predator, you'd think that it mostly ate the green species. So you can get that kind of dynamic change through time and also through space. So you can get quite dynamic diets come out of the model. In terms of the fisheries, we break it up by métier, and you can have fish with different behaviours. You can have some fisheries that just fish locally. You can have others that move around quite a lot, and that's superimposed on to that bigger spatial structure of where ports are, because that's where human recreational fishing pressure comes from. What a riverine inputs into the system, which include pollution. You can have large-scale climate shifts as well. So there's a lot of different ways of representing the human footprint, but the fisheries get the most attention. And that's broken up in the same kind of steps as you'd think about a feeding interaction. So you've got, it could be a vertebrate or invertebrate. It's just, what is it going to take? Then you've got the catchability. So that's a feature of the animal. How catchable am I by that particular gear type? It might be conditioned based on whether you're reproducing or not. You might go off the bite if you're reproducing, or you might become more aggressive and become more catchable when you're reproducing or at certain times of the year. Then you've got accessibility. So you're physically in the same location as the gear. Can the gear come into your habitats that you live in? It's to allow for fine and scale structure within the large polygons. And then you've got selectivity, which is a feature of the gear and can be changed based on management. If all of those line up and you're accessible and catchable and the selectivity can get your size, then you're caught. At that point, you have there is an escapement possibility. The proportion can be said to escape. And there's a proportion that can be said to be discarded, and either one of those can have some survivorship. Typically, escapement typically has 100% survivorship, whereas discards can have a much smaller percent. And then any discards that are dead go on to detritus. For each one of those, catchability, accessibility, selectivity, there's different curves that can be applied. And again, different for each species, or different, more likely for each fishery. and then you can have different values for discards and escape rates for different species per gear type and per fleet. So you can really try to tailor things into what makes sense for each part of the system. In terms of effort dynamics, that can be as simple or complicated as you want. You can just have a straight fishing mortality rate. You can have a straight amount of effort applied that fixed through time, or it can become much more elaborate. You can have interpolations on quarterly distributions, much like how you might do the simple fish movement. You can have a force time series from observations, or you can have more dynamic representations of effort that are allocated proportional to the CPUE. They can grow the amount of effort or decrease the amount of effort through time based on the catch per unit effort. So you sort of think of, you get more, if you're getting more catch than the upper bound, then, or the catch rates are up higher than the upper bound, you might put more effort into the system as more fleets, more fishing vessels enter the system. And if catch rates drop, then you might see the fleets disappear. You can also impose closures or buybacks of fishing. And as you can see on the right-hand side there, that's actually a case where we use that band of catch per unit effort and a closure of a system to external vessels to reproduce the pattern of fishing pressure in the northeast US. So a very simple model can represent the gross patterns of very complicated processes, and that's kind of the message behind Atlantis. As complicated and huge as it is, we have tried to keep each individual part relatively simple. And that's also represented by the recreational fishery, which just sort of says, okay, if this is a general human population growth trend in an area, what percentage of those humans go fishing? Now, the more dynamic effort can get quite a bit more elaborate, trying to bring in socio and economic drivers, distance to port, how long they want to be at sea, how they make their plans on an annual basis about when in the year they go fishing. Within months, are they actively going to follow that plan, or have they got something new that's popped up? Is there a new port that they can do? What state is their vessel in? Does it need maintenance? And then on a weekly or fishing trip basis, do they have quota in hand? What's the most valuable fish to target that they are allowed to target? Are they meeting their targets in terms of their economic targets? So it can be quite lively and detailed in a quasi-AB agent-based modelling approach. Most models don't go that far. I tend to personally have some models like that I've developed, but most people use a simpler representation, and that's fine. It's just saying that the options are there if you want. In those kind of cases, when you get to the actual fishing event, regardless of how you defined effort, it does tend to say, okay, what's the effort I can apply in this location? What fish are here? This is the catch that happens. For the more elaborate fishing events, they do step through a quasi-agent-based model logic, which is the effort supposed to be happening right now? Yes, then okay. Is the catch going to be profitable? Yes, then they'll go fishing. If it's not finding anything, they can switch methods, or they can try a new location. They can try and target other fish. So once again, it's kind of as elaborate as you want to make it, with most people tending to have the simpler, okay, once we've figured out how much fishing's happening in the cell, what's there, what do we catch? On the socioeconomic side, this is largely in there to help drive some of that more elaborate fishing behaviour, because it introduces the behavioural uncertainty. And some of that is economic motivation of trying to be profitable, and some of it is social drivers. What is your little friendship network doing? Can you share quota with them? Can you get information from them? In terms of the detail in that, it does try to think about cost structures around what are fixed and variable costs, like onshore costs and insurance and fuel, versus ice and crew wages and all those kind of things. And there are some simple market models in there too to try and give value to the fish if you're using those economic options. So those human behaviours can also be influenced by the socioeconomics, and that might be around how much quota you're going to buy or sell. In the case of Atlantis, it doesn't assume necessarily that you're trading quota for... we have individual transferable quotas in Australia, I should say. So that means that you can transfer in and out your proportion of the allowed catch. And so how you do that can be on a species-by-species basis, and most models assume that. But Atlantis mimics the process in Australia where you can sell bundles of quota across different species at once, which is socially and economically motivated. You're more likely to lease it out if it's... it's easier to lease it out rather than buy. That's a lot cheaper. But you're more likely to lease to a friend than to a competitor. Now, in terms of the investment, that's whether they invest in new boats or try to enter into fishing in a new sector, and that's based on what the expected profits are and actually their kind of behaviour. Are they someone who is an innovator or traditionalist? So once again, you've got that kind of agent-based approach to thinking about some of these aspects. In terms of the fishing management, it can represent all the different kinds of major management types. Again, completely configurable to what makes sense for your particular fishery, and it can be different for different fisheries. So you can have quota limitations, size-based rules around gear, spatial rules around marine protected areas and fishing zones, trip limits, rules around species of conservation concern, where they might close a fishery if you catch a few, discarding rules, you name it, it's in there in some form. So in terms of the assessment side of things, you've got different kinds of data collection. You've got industry-dependent reporting, which can be modified if the observers are on board. You can have you can use that to mimic camera monitoring now. That probably needs a little bit more finessing. You can have fisheries-independent data collection, so surveys where different kinds of data is collected on different scales with different degrees of robustness or skews, bias, error. So diet data can be patchier than biomass surveys, for instance. It can then do direct simple estimates of biomass, so do an assessment mimic, or you can couple to far more complicated assessment models like SS3, stock synthesis, Bayesian belief networks, that kind of stuff. It really depends on whether the assessment is the focus of what you're looking at or that bigger picture. You can represent other human sectors as well. Like I said, fishing is the focus, but you can represent pollutions, particularly contaminants and how they move through the food chain. You can look at the collision risk and noise pressures from shipping and dredging, and then you can impose footprints more than dynamic representations of things like tourism and coastal development and land use. There is a urban land use and dynamic population model for the humans, but that's kind of a Beth-only thing at the present moment. It's a bit still out there in trying to get it to work nicely, but that capacity is there. So lastly, sort of thing to touch on is uncertainty. So Atlantis is such a big model, you can't do a classic parametric or variant sensitivity analysis. It'd take longer than the universe existed to get it all run. Quite literally, I actually had a PhD student calculate that. So what you need to do is you need to define not just your strategies and your underlying scenarios like the level of climate change, but your model specification. And in doing that, you look at the most influential parameters or influential processes like feeding, diet connections, growth rates, that kind of stuff. And you do a little bit of a what happens if they're low, what happens if they're high, what happens if they're somewhere in the middle kind of specification across the entire food web. And then you generate your outputs for each strategy and scenario with those different specifications. So at a very minimum, you want optimistic, pessimistic, most likely versions of the world, but you can have a lot larger range of those specifications. I tend to have at least 10 or more when I'm thinking about some of these management strategy evaluations, but can get as elaborate as you like. But at the very simplest, you'd want to have a pessimistic version of the world where your productivity and biomasses are low, your habitat dependence is high, your recovery rates are low, your vulnerability is high, your sensitivity is high, So that's the most pessimistic version of the world, and then you have equally the most optimistic version of the world around things aren't affected very much in the first place, and then they recover really fast. Your central case is typically what you think is the best representation of the world, and your variance, your pessimistic and optimistic versus that version of the world. And it's not just per species, it's actually in the dynamics of the entire ecosystem. Now, the assumption and the hope is that reality falls somewhere in that range, from optimistic to pessimistic. So you do try to look at validation to make sure that you're covering that. So the functionality, looking at the most sensitive subset of parameters and structures, helps a lot. Bounded parameterization helps a lot. And then what I mean by bounded parameterizations is it's not just blind varying of parameters, it's what makes biological sense based on observational data, so that you're not trying to move beyond observations into purely made-up world. Another useful way of understanding the model structure and whether it's responding and what the uncertainty is to look at what's called perturbation analysis, where you intentionally shock the system with a large hit of fishing pressure or a huge temperature change to see that gross high-level shock response, to give you a sense of whether beyond its normal range of activities it does respond well. So you know how much you can rely on the tails of the distribution of your output versus the centre, the most common parts of the output, which aren't too different to where you set it up in the first place. So that's a very long-winded description of Atlantis and what it does, and hopefully you'll have lots of questions. Thanks.